random from 2.1 since they all were kind of. How about number 7?
2.1, number 7.
Each one of them like that. That's close enough to the book to be maybe some hope, but they're all.
All right. Oh, yeah, okay, so this is dealing with, these are quadratic in the dependent variable. And so there's sort of variations of that logistic differential equation.
Right.
Yeah, they're all sort of like
All
variations.
kind of
Let's do 7. 7 was the ugliest.
Yeah, I'm good.
7. You can do any of them. I believe. I think I circled number 7 and said ugly. Okay. All right. By the way, if you're coming in or you haven't done so yet, problem set 3 is due. Let's look at number 7 in here. 2.1 population models.
Oh, the first one's the.
And I wish I were taller, so I could use more of the board. But wish I was a little bit taller. Not to be a baller.
You could get like a step ladder and then just like kick it around the
All
board.
right,
As
so
you
we
go.
have.
I don't think. Yeah. I'm just saying.
So 7 dx dt equals 4x. 7 minus x, is that
That
right?
is right.
With the initial condition that x of 0 equals 11. Hopefully it's becoming a little less awkward to deal with independent or dependent variables that they call x. You know, we're used to seeing that as an independent variable, but oftentimes it's used as a position function or something like that, so x of t. All right, well, it is separable, and I would take all of this. This is a function of just x only. I'm going to take that part of it and leave the 4. Okay? So first step, separating these, I would write dx over x, 7 minus x, equals 4 dt. So I'm going to leave that 4 on the right side. You were there?
Before you,
How many people got there?
is there a difference between that way and moving all over and leaving a 1?
No, it'll just be some sort of integration multiple
Yeah.
when you're integrating
I
one
left
side.
the 1 over there, but I can see what.
Yeah, so I just left that constant over there. Now here's the part, well, if we pull that apart, we got 1 over x, 7 minus x, and this is the piece where we use partial fractions. Now the good thing about all these problems, as far as I can tell, the partial fractions weren't terrible, the partial fraction decomposition. Okay? There's a whole theory on them. If you have repeated linear factors, if you have an irreducible quadratic factor, all kinds of stuff, different cases. But these are just distinct linear factors. Okay? And if the degree of the numerator is less than the overall degree of the denominator, then it will break up somehow as a constant over the first factor plus some constant over 7 minus x. Yeah? So this is just side work. Now, if you imagine multiplying both sides by that x, 7 minus x, it's kind of helpful, you know, if you want to visualize that. X, 7 minus x. So on one side, that all cancels out, you just get 1 equals, and that when that thing distributes to each term, the first term is going to cancel the x's. I'm going to have a times 7 minus x. Plus, and equivalently, the 7 minus x would cancel there, I got px. Okay? I like to see my variables on the left, so I'm just going to multiply this out. I'm going to have 7a minus ax plus bx, and I'm just going to write that as plus bx minus ax. Right? That equals 1. Now, what I do is I factor out the x there, the variable, and this is a constant, b minus a, x equals 1. So this one's not too bad. It says, okay, for these to be equal, on the left side I have a linear thing in x. On the right side I have a constant. For these things to be equal, b minus a has to equal 0. 7a has to be that constant 1. And this equation right here implies that b has to equal a. So if 7a equals 1, we just get A equals 1/7. And since B equals A, we get 1/7 for that also. Okay? So that's the side work. Now, over here, I'm going to rewrite that. Oh, it's not 1, it's 1/7, right? 1/7 plus 1/7, and it was x 7 minus x dx equals 4 dt. So that's just the work we did over here. Now, one thing is, I don't want to leave those in the numerators. That would be just dumb. Well, it wouldn't be, but I can pull out the 1/7, and you can multiply both sides by 7 now, or after you integrate it. It doesn't matter, right?
Do it now.
Do it now. It does. Integrals are linear operators. I can integrate and then multiply both sides by 7. And what do we get on the left side? And I know I'm going to get natural log 7 minus x. The thing is, though, the derivative of natural log 7 minus x will be 1 over 7 minus x times the derivative of the argument as a -1. So it's going to, I have to put a negative out here to counteract that. When I go through the chain rule and multiply both sides by -1, it's going to knock that out. Makes it
You want to
positive.
combine them into a ln division.
And on the right, I'm imagining I multiplied both sides by 7. So we're going to have 7 times 4t, or integral of 28, which is still 28t, plus, and imagine any constants from over here, any constant from over there, just combine them. Okay, and then properties of logs says this is log of the difference, same base, is log of this over that. Okay, so we're using everything. Everything from every class you ever had. All right, equals.
No geometry yet.
Yeah, no geometry, that's right. 28t plus c, and then we apply to get rid of, to undo the log, apply the exponential function, both sides. All right, and then I'm going to squeeze one more line in here. Those knock each other out, and technically, this technicality, I have absolute value x, and e to the 28t, right? Plus c means it's e to that times e to that. I could pull that e to the c out here, and I could just call it whatever, c1, a, whatever you want to call it. Now, here's the deal with the absolute values. At this point, if I drop the absolute values, not knowing if this is positive or negative, I have to put positive or plus or minus c1 e to the negative, or e to the 28t, yeah? So drop those, and I'm just going to call this a, e to the 28t, where a equals plus or minus c1. So a could be a positive or a negative constant, depending on the sign of that ratio. All right, we're almost there.
Condition.
What's that?
We have an initial condition.
We do, and you can put it in early, or you can put it in later. So input represents t. You gotta be careful because it's so tempting to put 0 in for x, right? Because that looks like our independent variable. Okay, but we gotta be careful. X takes on the value 11 when t is 0. All right. So you can put the condition in now. 0 for t, and x for 11. That would allow you to solve for a. That's not so bad, huh? So the initial condition, x of 0 equals 11. That's t, that's x. So we can solve for a pretty easily because I've got all this right here. So e to the, well, that would turn out to be 0. I have 11 over 7 minus 11 equals, that's the x. T, when t is 0, we just get equal to a. Right? Good. So what is this?
Negative 11/4.
Negative 11/4. So it turned out to be negative. Okay. All right. So at this point we got x over 7 minus x, putting this back in, equals negative 11/4 e to the 28t. And then if we want to solve this for x, that's the thing. This is implicit, right? But we can solve this for x by multiplying both sides by the denominator, 7 minus x. So x of gonna be equal to, I'm gonna put that in front, 7 minus x times negative 11/4 e to the negative 28t. Oops, not negative. Okay. And if you distribute that to both sides, we get x, and I better write this out, that's gonna be negative 77/4 e to the 28t, and be careful, minus, and this is a negative 11/4, so it's gonna be plus 11/4 x e to the 28t. Now, this term also involves x, so it's nice just to get it to the other side, or get that one to that side. I'll get this one over here. So we have 11/4 x e to the 28t equal, oh, not yet, minus x. I'm just rearranging that, and this one's negative, so I'm gonna put it on the other side of the equation to be positive, equals 77/4 e to the 28t. Okay, and then we're able to factor that x out. Okay. Well, divide both sides by that. Pull out the x, we got 11/4 e to the 28t minus 1. So divide both sides by that quantity, and we get x equals 77/4 e to the 28t over 11/4 e to the 28t minus 1. Now, the book has something that probably looks different than this, because they clean things up. I'm noticing they clean things up in a very particular way.
Right, and this doesn't seem overly
Yeah.
intuitive how they get there.
Yeah, what I'm gonna do is multiply numerator and denominator by 4/4, just to knock out these
You
denominators.
get a negative 2018 in there.
Yeah, so we're gonna have 77 e to the 28t. And I should say, well, yeah, we're multiplying by 4. And when this 4 distributes here, it's gonna knock that one out. I'll have 11 e to the 28t minus 4. And then what they do is they don't leave these e's up there in the, if I multiply numerator and denominator by e to the negative 28t, then again, up top, when you multiply those, the exponents add to 0, right? E to the 28t minus 28t. So you get 77, and in the bottom, when this distributes to this term, same thing happens. 11 e to the 28t times e to the negative 28t just gives me 11. Minus, and this is going to be 4 e to the negative 28t. So that's, and explicit as a function of t.
Could you leave it in the form you have it one step back, you said, already explicit? You've already got an x of t equals, you just didn't do that.
Oh, right here?
Trick. I mean.
Yeah, would I care about that? No.
That's
No. Like I said, I mean, is there any objective place to stop? I mean, yeah, you could argue that you think this looks prettier, but it's no more correct than this.
Where did you get that second e to the 28t?
This one down here?
Oh, you distributed it across the other side.
Oh, this guy. This guy?
Oh, no, back on the other side, I was realizing maybe you distributed.
Oh yeah,
across the
I
side
distributed
minus
it right here too. So negative
Yeah,
77/4
so
e to the
it's
28t minus negative 11/4 x e to the 28t.
Could you just flip like invert both sides when you have it the x over 7 minus x? Or am I missing another trick? Can you do the inverse of both sides and get negative 4 over 11?
Yeah. If you recognize what's exactly in the numerator and what's in the denominator over 4, you know, something like that, and then you invert both.
And then split it out. Okay. I was just wondering all of a sudden when I looked up and I was like, there's 2 of them now. These.
Just looking at some of the answers they have, you know, I can kind of see the route they take to their simplified version where they stop. Okay. The one nice thing about this version is that there's only one exponential factor anywhere in that, as opposed to up here, down here. you can find the limit as well, you know. The one thing that's nice about this, again, is that as t goes to infinity, you can see this e to the negative power. Well, e to the negative infinity, that's approaching 0 asymptotically, so this term drops out to 0, and the limiting would be 77/11ths, right? You can kind of also see that over here, because e to the 28t is a massive term, massive amount, right? But we got e to the 28t down here, -1. That is totally insignificant compared to the magnitude of these two terms. So it's almost like that, as t goes to infinity, you know, those cancel out. 77/4 over 11/4, that's just 77/11ths.
7.
Hmm?
7.
77/11ths.
7.
Sorry.
77 divided by 11 is 7.
Mm-hmm. 77/11ths is 7. Okay. So yeah, those are good practice because they're all just slight variations of each other. Those ones, you can get that idea. And on an exam, there wouldn't be, you could expect in class not to have to do anything more complicated than that as far as partial fractions. Yeah, there may be two terms. This one was nice because you end up with just 7a has to equal 1. And Justin?
Yes.
Yeah, your idea before, that also works. When you see this, you let x equal 0, it zeroes that out, you obviously get 7a equals 1. So this one's nice because you got an equation in 2 variables, but well, this one only has 1 variable, so you solve it right away. Some of them might be two equations in 2 variables. Yeah. Okay. Just a show of hands, anybody trying to use, or having luck with D field, using that? Anybody used it? Anybody?
I haven't tried.
I tried. I'm not getting anywhere with it.
Didn't seem so necessary for the last few.
Yeah, some of them they give them to you. There is a way to do it with the calculator. I messed around with that and got it to work.
Yeah.
All right.
Yeah, it's not very stiff on it.
Well, it's okay. It's not terrible. It's not as bad as I thought it would be. The graphics. All right. Let's go ahead and get started then.
It's not doing it itself.
You can sit here next time. I'll sit back there.
We're actually going to be looking at another approximation method today.
Oh,
but
no,
instead
I'm
of
cool
a
here, actually. I
practical
can't
method
sit
of
further up.
approximating a curve or visualizing a curve, we're going to be looking at a numerical method to approximate solutions to a differential equation. All right, but first, before we get to that, we're going to talk about 2.3, and this is just a, well, comes a little back to acceleration, velocity, and position. Just when we thought we knew everything about that.
So do we have an additional homework set that you haven't given us? Because we have 2.1 and 2.2.
2.1 was the mathography. And then
2.1 was the mathography.
2.2 was the one we turned.
Problem set 1, it was called problem set 1.
No, what I mean on the sections. On the sections that you give us homework.
No, so the problem set, it did not have problems from every section in the book, right?
Okay.
Okay, yeah. All right. So we're going to be looking at, what's today? Thursday? 4/17. All right, day 6. All right, so we are going to be revisiting, but with a little bit more accuracy. All right, so section 2.3. Acceleration, and I'm just going to abbreviate that. Acceleration, velocity, and position again. Now, acceleration, I'm just going to define them right here. We are using a of t, acceleration at time t. Velocity, we're going to stick with v. And position, we're going to call it h or no, sorry, y, just height. So it kind of corresponds with our idea of height. But this could be linear, linear displacement horizontally, it could be up and down, so that's our displacement. All right. So Newton's second law, we're going to start from there. He was bored during college and came up with all the physics laws in between semesters. But, force equals mass times acceleration. All right. So first case we're going to look at, and this is vertical motion, and this is ignoring air resistance, which we've already done. Okay, so this force equals mass times acceleration law becomes, well, mass times acceleration. Acceleration is dv dt. And when we're talking about a falling body with no other, what's the force acting on it? Gravity. So I'm going to just call that gravity. So ignoring air resistance, the only force acting on that body is gravity. And that could be, well, the force of gravity. And I'm putting a sign on it because if we assign vertical direction as positive, then gravity acts exactly opposite to it. So it would be negative mg, where g is constant due to gravity. Okay. All right. Now, dividing both sides of that, of course, by m, you notice that those cancel out, and we would get dv dt equals negative g. G is a constant, depending on, what plane you're on or whatever. So that should be familiar. And we've already seen this, but just a reminder of what the situation is when we disregard air resistance. We get, well, if dv dt is negative g, we get v. Well, I just integrate both sides. This is integrable. And we get negative gt plus, I'm just going to jump right to that and call it v naught, because when 0 is substituted for t, that number represents the initial velocity at time 0. Okay, so usually we call that constant v naught. And of course, going one step further, the position or height, negative gt squared over 2 plus v naught t plus some other constant, but we know that when t is 0, it drops those ones out, so that constant refers to the initial velocity at time 0. We call that, oops, not the initial velocity, but the initial height. Okay. So this is with v naught is the same as the velocity at time 0. Y naught is the position or height at time 0. All right, so we've seen that before. These are the famous ones you see. Well, if g is the force of gravity and it's 32 feet per second, you get negative 16 t squared plus initial velocity times t plus initial height. Right, seen that. We're doing that in Math 60, talking about where a rocket is after 2 seconds after takeoff, things like that. Right? We don't tell them where it comes from. All right, but one thing, that's ignoring wind resistance, which is not very practical when you have atmosphere. Yeah? So we're going to take that into account. That's going to be the new business. So secondly, vertical motion with air resistance. All right. So we're going to talk about the force, and it's a resistance, it's a force. If something is falling, if we're talking about something in free fall, well, it's going downward, gravity's pointing downward, but which way is the force of wind resistance acting on it? Straight upward. So it's opposite of the direction of gravity. So we could call it, and the book calls it F sub R, R for resistance. Now, if we assume, okay, and there's different models, but if we assume that the resistance due to the air is proportional to the velocity of the body that's falling, then we get this thing right here. Proportional to the velocity, K times V, right? But let's think about this for a second. If the velocity is negative, meaning it's going downward, then the force of wind resistance is acting upward, so it should be positive. So think hard for a second. If V is negative, this force should be positive. Well, yeah, you could think of K as a negative constant, but just to keep K negative, we have to put a negative out there. Here's why. Yeah, when V is negative, in other words, when it's coming down, negative K times V, negative V would be positive. This would be acting upward. So opposite the direction of the, opposite the sign of the velocity. On the other hand, if the velocity is upward, if I throw a ball, there's still wind resistance, right? Okay? So I throw something upwards, its velocity is positive, but which way is the wind resistance acting on it? Downward, so it should be negative. If velocity is positive, I should get a negative constant, a negative value. So we're going to take K to be positive, and we're going to put a sign in front of it. So this is opposite it. All right, opposite the direction of the velocity. Okay, so that sign is a little bit misleading, but when V is negative, wind resistance is acting in the positive direction. It's exactly opposite to the wind. So, going back to Newton's law, mass times acceleration, acceleration is the rate of change of velocity, we get, there's two forces, gravity is acting one direction, wind resistance is acting in the opposite direction. Now, it looks like they're both being added together and they're going in the same direction, but when we put these in here, we just talked about this. This is negative m times g, and F sub r is minus kv. Okay? Again, they're not going the same direction because if this thing's going downward, velocity is negative, this term is actually a positive. It's adding. So you got gravity acting downward on this, where g is the positive constant of gravitational constant, 32 feet per second. If this thing's going down, then it's actually going the opposite direction of the object. Okay. All right. So dividing both sides of this by n, we get dv dt equals, the m will cancel there, I'm going to get negative g minus k over mv. So that's just dividing through by m. All right? And then one substitution, that k over m is a constant, and the book just calls that rho. Again, it's just that sort of little trick of gathering together things that are constant and calling it something new so it looks simpler. All right? So that's a linear equation involving V, and it does not involve, notice it, the right side does not involve the independent variable time. So it's an autonomous equation, meaning regardless of the time, if I drop an object, wind resistance is going to act on it exactly the same, whether it's t equals 0 or t equals 10. That height function would be the same, but just translated over 10 seconds. All right, so I'm calling this equation 1. All right, now, so equation 1 is separable. Just because of the fact that there's no t over there. So what would it look like if I separated this? I could factor a -1 out of those terms as well. But it'd be just, I could divide the whole thing by, get that whole expression over there, down here. But what I'm gonna do is factor a negative out, and this would be G plus rho V equals, and I'm gonna leave that -1 hanging out, kinda like I left a 4 on the other side, a constant. And this would be negative dt. Okay, so factor out a negative from that and divide by G plus rho V. All right, now we start the process. We integrate this. I'm gonna get a different color. I like colors. Something for your eye to just be, kind of catch when you're reading over these notes. All right, so we're gonna integrate both sides. And this is kind of tricky, but what am I gonna get on the left? It's gonna be a log function. That's the variable with that we're integrating with respect to. So that's with respect to v. So it's going to be like a natural log deal, and it's going to be natural log g plus rho. That looks like a p. Rho v.
All divided by rho.
Right, because if you go in reverse and differentiate this, it would be 1 over g plus rho v times the derivative with respect to v, which is rho. I don't have anything like that over here. I'm going to get a rho, so I need something that's going to cancel that out. 1 over rho over there. Okay, so that's just the constant going to pop out. Equals, on the right side, well, that's just pull out a -1. I'm just going to get negative t plus c, some constant. All right. I'm going to multiply both sides of this by rho now. Get rid of that. Rho. And we get natural log g plus rho times v equals negative rho t plus, and I'm just going to call this a new constant. Is that okay? Rho times c, whatever that, those are just two constants. I'm going to call it c1. Tracking them over here, but it's not terribly important. Okay? It's just a simplifying step, so it's trying to suppress all these different looking constant terms. Okay, so if I want to be able to solve this for v, well, I got to get rid of the natural log, so we use the exponential function, apply that to both sides. And what does the left side become? Yeah, and we get absolute value. Again, I'm going to write without the absolute value, g plus rho times v equals, and I'm going to have this exponential term, e to the negative rho t, times e to the c1, but I'm going to call this a.
You're outside.
We outside of that?
Yeah.
All right. And this is where a is technically a positive. E to the c1 is always going to be a positive. But if I drop those absolute values, I don't know if the left side is negative.